Hi, and welcome back to Statistics. Today we're going to be talking more about regression. But first, let's begin by reviewing the main topics from the last lecture. In the last lecture, we discussed how every regression line has two equations. The unstandardized regression equation, which uses raw scores, and the standardized regression equation, which uses z-scores. Raw scores are also called unstandardized scores, and z-scores are also called standardized scores. As an example, we used this scatter plot, which shows the relationship of fertility with life expectancy in about 100 countries. Each dot represents a country. Now, here's the regression line for this data. The line has a negative slope, and this is the unstandardized regression equation for the line. Now, we can use the equation to find the predicted life expectancy for a particular country. For instance, suppose the fertility in a country is 5. That is, the value of x equals 5. We can plug this number into the regression equation, and when we do the algebra, we find that the predicted life expectancy in that country is 58.5. 58.5 is the same number we get if we plot the prediction point on the regression line. Now, this regression line also has a standardized equation, and we can use it to make predictions using the z-scores. For example, suppose a country's z-score on the x variable is 1.57. This z-score is equivalent to a raw score of 5. And we can plug 1.57 into the standardized regression equation. And then when we do the algebra, we find that the predicted value of the z of y is negative 1.26. Negative 1.26 is the same number we get if we plot the prediction point on the regression line and then use the point to find the predicted value of the z of y. Now, as we said, 1.57 is the z-score equivalent of a raw score of 5, the prediction point on the regression line that is shown in this scatter plot. Oh, excuse me, the prediction point on the regression line that is shown in this scatter plot is the same prediction point that we find if we use a raw score of 5 as our predictor. And this example shows that the unstandardized regression equation and the standardized regression equation use the same regression line, have the same prediction point, and produce the same predicted value of y. Now, the only difference is that one is using the unstandardized values of the variables, and the other uses the standardized values. Now, in the last lecture, we also learned some new terminology. In the unstandardized regression equation, the number that is multiplied times x is called the unstandardized slope. And it's also called the unstandardized regression coefficient. And the mathematical symbol for the unstandardized regression coefficient is b. The number in this part of the equation is called the unstandardized intercept. Now, the mathematical symbol for the unstandardized intercept is a. Now, we said that in analytical geometry, which you learned in high school, the slope is m and the intercept is b. But in regression, the symbols are different. The slope is b and the intercept is a. Now, next, we talked about the terminology for the standardized regression equation. The number that is multiplied times the z of x is called the standardized slope. and it's also called the standardized regression coefficient. Its mathematical symbol is the Greek letter beta. Now, the intercept of a standardized regression line is 0, always. But the 0 is never shown. It's an invisible presence. Now, in the last lecture, we also introduced two essential facts about the standardized regression equation. In a standardized regression equation, beta, the slope, is equal to r, always. And the standardized regression equation can be written in two ways. In the first version, the predicted value of the z of y is equal to beta times the z of x. In the second version, r is substituted for beta, so the predicted value of the z of y is equal to r times the z of x. And these two equations are equivalent. But this second form of the equation is extraordinarily important, and we call it, for that reason, we're calling it the magic formula. Now, I showed you how the magic formula can be used to solve regression problems. First, we learned how the formula can be used when the predictor and the criterion are z-scores. Now here's an example. Isabel had a z-score of 1.50 on the midterm. Estimate Isabel's z-score on the final. Now in this example, the criterion, the thing we want to predict, is Isabel's z-score on the final, and the predictor is her z-score of 1.50 on the midterm. Now, for this kind of problem, we're given only one piece of background information. The correlation of midterm grades with final grades is 0.50. Now, we use the magic formula to solve this problem. We're given the information that r equals 0.50, so we'll substitute 0.50 into the equation. We're given the information that Isabel's score on the midterm is 1.50. So that means that Zx is equal to 1.50. So we substitute that 1.50 into the equation. Then we just do the math. 0.50 times 1.50 equals 0.75. And that's our answer. Isabel's predicted z-score on the final exam is 0.75. Now next, in the last lecture, we showed you how the magic formula can be used to solve regression problems in which the predictor and criterion are raw scores, that is, when they're unstandardized. And here's our example. Carla scored 90 on the midterm. Estimate her grade on the final exam. Now, in this example, we have two variables, midterm and final exam. The one we're asked to estimate is the final exam, so that's our criterion. And her grade on the final exam is the criterion, and the other variable, her score on the midterm, must be the predictor. Now, for this type of problem, we're usually given a fair amount of background information. First, we're given the mean and standard deviation of the predictor, x. Second, we're given the mean and standard deviation of the criterion, y. And finally, we're told the correlation between x and y, which in this case is 0.50. Now, we'll use this box to help us solve the problem. We need to fill in the numbers one by one from left to right. The idea is that we turn x into a z-score, then use the magic formula to find a solution that is a z-score, and then turn that z-score into a raw score. So we know Carla's raw score on the predictor x is 90, so we write that here. Next, we need to turn that raw score into a z-score. And we turn that into a z-score of 1.5. To do this, we just use the same formula we always do. Z equals the deviation divided by the standard deviation. And next, we use the z of x to calculate the predicted value of the z of y, which is 0.75. And we do this using the magic formula. So now we have our answer almost. The problem is that the answer is in z-score form, but we need to turn it into a raw score. So to get this raw score, we use this formula, which we learned about a month ago. So now we have our answer. Carla's predicted grade on the final exam is 82. Now finally, in the last lecture, we learned how to use the magic formula to solve regression problems in which the predictor and criterion are percentiles. And here's an example. Misty's midterm score was at the 95th percentile. What was her percentile on the final exam? Now in this example, we have two variables, her percentile score on the midterm, her percentile score on the final exam, and we're asked to find or estimate her percentile score on the final exam. So her percentile score on the final exam is the criterion. The predictor is the midterm scores, is the percentile scores on the midterm. Now for this kind of problem, the only background information we're given is that the correlation of midterm grades with final exam grades is 0.50. Now we'll use this box again, which is a lot like the one we used for the problem involving raw scores. Again, the idea is to turn the predictor into a z-score, use the magic formula to get a solution for the predicted value of the z of y, and then turn this z-score back into a percentile. So Misty's percentile on the midterm is 95. So we put that up here. Next, we need to turn the percentile into a z-score. The only way we can turn a z-score into a percentile is to look at the table, which you're already familiar with. So a percentile of 95 is equivalent to a z-score of 1.65, according to the table. Now it's time to use the magic formula. So when we use the magic formula, we can see that the predicted z-score of y is 0.83. Now again, the problem is that this is a z-score and we need a percentile. So to turn it into a percentile, we use the table again for equivalent z-scores in percentiles, and we find that Misty's predicted percentile on the final is 80. Now at the last lecture, we also learned a second essential regression fact. The regression, and that's that the regression line always goes through the point of averages. So this means that the point 0, 0 is always, okay, so give me just a sec, I got here. So this means that the point 0, 0 is always on one of the points on the regression line if we're using standardized coordinates. And the point whose coordinates are the mean of x and the mean of y is always on the regression line if we're using the unstandardized coordinates. Okay, so that's it for the review of the last lecture. Now we're ready to cover the new topics for this lecture. We'll begin today's lecture by discussing the similarities and connections between the z-equal line and the regression line. So let's begin with the positive z-equal line. Now, as you remember from previous lectures, this is the standardized equation for the positive z-equal line. The z of x is equal to the z of y. And here's a picture of the positive z-equal line. For every point on the line, its first standardized coordinate is equal to its second standardized coordinate. So the point 1, 1 is a point on the line. Point 5 is another point on the line. 0, 0 is another point. Negative 0.5, negative 0.5, and so on. It just goes on this way with all the points. The first coordinate and the second coordinate are always equal to each other. Now, we can see that the positive z equal line goes right through the point 0, 0, which is the point of averages. And that's an important thing to recognize. The positive z equal line goes through the point of averages, always. Now, it's important also to know the slope of the positive z equal line. Let's take a moment to calculate it. Remember, we can always find the slope of a line if we know the coordinates of 2 points on the line. Here are 2 points on the line, 0, 0, and 1, 1. Now, using these 2 points, let's calculate the slope. We'll begin with the rise. For the rise, we use the y-coordinate of the y-coordinates of the 2 points. And the rise is 1 minus 0, which equals 1. Next, we'll use the x-coordinates. So let's see. Yeah, we'll use the x-coordinates to get the run. And the run is also 1 minus 0, which equals 1. And finally, we get the slope by dividing the rise by the run. 1 divided by 1 equals 1. And that's our answer. The standardized slope of the positive z equal line is 1. Now, let's compare that with the regression line. As you remember, one of the important facts about the regression line is that it always goes through the point of averages. And its standardized, its standardized slope is beta, and beta is always equal to r. So now we see something about the regression line and the positive z equal line that they have in common. They both go through the point of averages. Whenever we have a regression line, we know it hits the positive z equal line at the point of averages. And there's an easy way to tell which is which. The positive z equal line is always steeper than the regression line. Well, almost always. We'll get to the exception in a minute, but most of the time this is true. And I want to add that what we're saying right now applies if the regression line has a positive slope. We're talking about a positive z equal line and a regression line with a positive slope. We'll get to the negative part in a minute. So let me show you what I mean about the positive z equal line being steeper. This graph shows the regression line and positive z equal, and the correlation of x and y is 0. The blue line is the regression line. When r equals 0, the standardized slope of the regression line is 0, and so the regression line is flat. The red line is the positive z equal line, and as you can see, it's definitely steeper than the regression line. Now, let's see what happens as the correlation increases. Here's a correlation of 0.10. Notice that the regression line went up slightly. Here's a correlation of 0.20, and here's a correlation of 0.30. The regression line is going up bit by bit, and the data points in the scatter plot are getting closer to the positive z equal line bit by bit. Okay, now here's a correlation of 0.40, 0.50, 0.60. The regression line keeps going up and up. The data points get closer and closer to the z equal line. 0.70, 0.80, 0.91. Now, when the correlation is 1, the regression line and all the data points lie on top of the positive z equal line. So what we've just seen is that the regression line gets closer and closer to the positive z equal line as r gets closer to 1. The positive z equal line is almost always steeper than the regression line. There's only one exception. When r equals 1, the regression line and the positive z equal line are identical. In other words, when r equals 1, the standardized slope of the regression line is 1. That's the same as the standardized slope of the positive z equal line. So both lines have the same slope and are identical to each other. Now, so far we've been talking about when the regression line has a positive slope. Now let's talk about a regression line with a negative slope and how it's related to the negative z equal line. So here's a scatter plot where correlation is 0. The blue line, the regression line, is flat because its slope is 0. R equals 0. The red line goes down from left to right and is the negative z equal line. Now the correlation of x and y in this slide is negative 0.10. The slope of the regression line has changed slightly, and the slope is negative, going down from left to right. And here are correlations of negative 0.20, negative 30, and negative 40. The regression line slope gets more and more negative. The data points are getting closer and closer to the negative z equal line. Now here are correlations of negative 0.50, negative 6.60, negative 0.70, negative 0.80, negative 0.90, and negative 1. As you can see, it's a mirror image of what happened with the positive regression line. The regression line, the regression line with a negative slope gets closer and closer to the negative z equal line as r gets closer to negative 1. The negative z equal line is almost always steeper than the regression line. The one exception is when r equals negative 1. When r equals negative 1, the regression line and the negative z equal line are identical. Okay, so that completes our discussion of the relationship between the regression line and the positive and negative z equal lines. Next, we're going to discuss how to calculate the unstandardized equation of the regression line. Now, you know how to calculate you already know how to calculate the standardized equation of the regression line. That's what the magic formula is about, that the predicted z of y equals r times the z of x. But how do you figure out the unstandardized equation of a regression line? That's what we're going to cover today. Now, to calculate the standardized regression equation, you need to know these 5 things. The mean and standard deviation of the criterion, y, the mean and standard deviation of the predictor, which is x, and the correlation of the criterion and the predictor. You notice I wrote the correlation coefficient a bit differently here. It's the letter r with subscripts of x and y. Sometimes the correlation coefficient is written using this mathematical notation. The subscripts are used simply to indicate what variables are being correlated. In this case, r with subscripts of x and y simply means what we've been calling r, the correlation of x and y. Now, here is the regression line whose unstandardized equation we need to find. And here are the 5 pieces of information we need to figure out the equation. There's the mean, standard deviations, and R. And the question is, well, before we get started, what is the standardized regression equation for this line? Think a minute to ask yourself, what is the standardized regression equation for this line? You do know how to figure it out. Okay, if you're thinking about it, here's it. Remember the magic formula, okay? So what's the standardized regression equation? Okay, here's the answer. Here's the magic formula. And up here it tells us that R equals 0.50. So we just plug that number into the magic formula and we know the standardized equation of this line. It's the predicted z of y equals 0.50 times the z of x. So now we're going to calculate the unstandardized equation. The unstandard equation is more complicated. Now, as you remember, to calculate the equation of a line, there are 4 steps. We find 2 points on the line. We use them to calculate the line's slope. We then calculate the intercept, and then we plug the slope and intercept into the general equation for a line. Now, when we're calculating the unstandardized equation of a regression line, we can actually skip this first step and just calculate the slope. And we can calculate the slope with an equation. And here's the equation. The unstandardized slope of a regression line is equal to R times the standard deviation of y divided by the standard deviation of x. Now, I'll show you how this works. I said we need these 5 numbers to find the unstandardized equation, and we're going to use 3 of them now. Down below here, we can see that the standard deviation of y is equal to 10. We can plug that number into the equation like that. Similarly, down below, we can see that the standard deviation of x is 0.40. And we can plug that number into the equation also like that. Finally, down below, we can see that R equals 0.509. So we can plug that number into the equation like that. Then we just do the algebra. First, we multiply the 2 numbers in the numerator times each other. 0.50 times 10 is 0.5. So we substitute 5 for 0.50 times 10, and then we divide 5 by 40, and we get the decimal fraction of 0.125, and that's the slope. Now, we did it all using this equation. Now, I'm sorry to tell you, but this is one of the equations you must memorize. You're going to need it again and again in this course, and you have to have it memorized. Okay, now that we've calculated the slope, we need to go on to the next step and calculate the intercept. Now, as you know, to calculate the intercept, we need 2 things. First, we need the slope. Second, we need to know the coordinates of a point on the line. Now, we just calculated. The slope is 0.125. So we'll write it here. But what do we do about finding a point on the line? How can we find the coordinates of a point on the regression line? Well, here's where one of our basic regression facts comes in handy. The point of averages is always on the regression line. And how do we find the coordinates of the point of average? Well, here are those 5 numbers I said we'd need. We're about to use 2 of them. The unstandardized coordinates of the point of averages are 420 and 75. That's because the mean of x is 420 and the mean of y is 75. And we know this point is on the regression line because the point of averages is always on the regression line. So now we have a point on the line and the slope. Now we just do what we learned to do several weeks ago. We simply plug these numbers into the general equation for a line. We take the x value of the point, which is 420, and substitute it for x in the equation. We take the y value of the point, which is 75, and substitute it for y in the equation. And finally, we take the slope, which is 0.125, and we substitute it for the slope in the equation. Now, we just do the algebra. 0.125 times 420 is 52.5, so we substitute 52.5 into the equation. Then we subtract 52.5 from both sides of the equation, and we find that the intercept is 22.5. So now we have the slope and the intercept, and we're ready for the final step of finding the line's equation. And this all involves calculations you're very familiar with by now. The slope is 0.125 and the intercept is 22.5. Now all we have to do is plug these numbers into the general equation for a line, like this. And now we have the unstandardized equation for the regression line. Y predicted equals 0.125 times x plus 22.5. So let's summarize what we've just done. Here are the steps for calculating the unstandardized regression equation. First, we use this equation to find the unstandardized slope. Next, we use the slope and the point of averages to find the intercept. And third, well, you know the rest. It's the first 2 steps that are kind of new, but the rest you know how to find the equation for a line once you have the slope and the intercept. Okay, now we're going to talk more about this equation for the unstandardized slope of the regression line. It's important to understand where it comes from and why it works. So we're going to see why this equation makes mathematical sense. That is, we're going to show that the unstandardized slope of a regression line really is r times the standard deviation of y divided by the standard deviation of x. And to do this, we're going to use facts and ideas that we've learned during the past few weeks. So let's review a few of these facts and ideas. First, let's do a brief review on the point of averages. When we make a hybrid scatter plot of group data, we can draw a vertical line to show the mean of x and a horizontal line to show the mean of y. The place at the center where they meet is called the point of averages. The point of averages is always on the regression line. The standardized coordinates of the point of averages are 0 and 0. And its unstandardized coordinates are equal to the mean of x and the mean of y. Now, here are the standardized coordinates of the point of averages, 0 and 0. And here are the unstandardized coordinates of the same point, which are the mean of x and the mean of y. If we start with the z of x, which is the first standardized coordinate of the point of averages, we can use it to find x, which is the first unstandardized coordinate of the point of averages. And we'll use the equation for transforming a z-score into a raw score. X, that's the raw score, is equal to the z of x times the standard deviation of x plus the mean of x. Now, we've used this equation many times before to transform a z-score into a raw score, so we know how to do this. We know that the z of x in this case is equal to 0. So we substitute 0 in place of the z of x in the equation. And so now we have a new equation. X is equal to 0 times the standard deviation of x plus the mean of x. Now, of course, 0 times the standard deviation is equal to 0. So we can simplify the equation. And our new equation is x equals 0 plus the mean of x. Now, of course, 0 plus the mean of x equals the mean of x. So we can simplify the equation even more. And our new equation, our final equation, is x equals the mean of x. So this proves that the first unstandardized coordinate of the point of averages really is the mean of x. Okay, so we just went through that to show how you could use the z of x to find x. Now, we could repeat the same process to prove that the z of y is, which is 0, and that y, that is the raw score, is equal to the mean of y. But we'll just skip that. It's the same thing as for x anyway. So instead, let's review another topic that we covered earlier, finding the slope of a line. Now, to calculate the slope of a line, we need 2 points that are on the line. The slope of the line is equal to the rise between the two lines divided by the run between the two lines. For instance, suppose we know that the point 3, 2 and the point 9, 4 are on the line. 3, 2, 9, 4. The rise is the vertical distance between the 2 points. In this example, the rise is equal to 2. And the rise, if we want to calculate it, is equal to the y-coordinate of the right point minus the y-coordinate of the left point. The run is the horizontal distance between the 2 points. In this example, the run is equal to 6. And the run is equal to the x-coordinate of the right point minus the x-coordinate of the left point. The slope is equal to the rise divided by the run. Now, in this example, the rise is 2 and the run is 6. So the slope is equal to 2 divided by 6, which is equal to 1/3. So this example demonstrates something we'll be using in a moment. If you know 2 points on the line, you can calculate its slope. So that's the end of the review. And now we'll turn to the main topic we need to discuss, finding the unstandardized slope of a regression line and showing that the slope is equal to r times the standard deviation of y divided by the standard deviation of x. Now, to find the slope of the regression line, we need 2 points on the regression line. For one of the points, we'll just use the point of averages. The point of averages is always on the regression line. Now, during the review, we saw that the standardized coordinates of the point of averages are 0, 0, and the unstandardized coordinates are the mean x and the mean of y. And here's a scatter plot with the point of averages on the regression line. The axis on the bottom of the scatter plot shows the z of x, and the axis on the left side shows the z of y. The point of averages is the point where the z of x equals 0 and the z of y equals 0. Okay, now next, we're going to need a second point. So let's use a nearby point. This its first coordinate is 1. That is, the z of x is equal to 1. So it's pretty close to the point of averages. Now, we don't know what the z of y is here. But because this point is on the regression line, we can figure out what the z of y is. We'll just use the magic formula. So the predicted value of the z of y is equal to r times the z of x. And we know that because this is the equation for all regression lines, standardized equation. Now, we just said that for this point, the z of x is 1. Just plug that number into the magic formula like this. So now we have a new equation. The predicted z of y is equal to r times 1. Now, of course, r times 1 is equal to r. So we can simplify r times 1 just plain r. And now we have a new equation. The predicted z of y is equal to r. Well, this is our answer. The z of y is equal to r. So we'll just write it up here. The z of y coordinate of the point is r. So for this point, the z of x is equal to 1, and the z of y is equal to r. Put another way, the standardized coordinates of this point are 1 and r. And we're going to give this point a name just to help us remember it. We'll call this point the 1r point. So this is an important moment. We now have 2 points on the line. The first point is the point of averages, whose standardized coordinates are 0 and 0. The second point is the 1r point, and its standardized coordinates are 1 and r. Now that we have 2 points, we can calculate the slope of the regression line. But there's one small catch. We want to calculate the unstandardized slope of the regression line. And to do that, we need the unstandardized coordinates of both points. But we don't know the unstandardized coordinates of the 1r line, 1r point yet, right? We don't know its standardized coordinates are 1 and r, but we don't know its unstandardized coordinates yet. So before we go any further, we'll calculate the unstandardized coordinates of the 1r point. And we'll start by calculating the value of x, which is the first unstandardized coordinate of this point. We know something that's going to help us. The z of x for this point is equal to 1. So we just need to transform this z-score, 1, into a raw score. We'll use the equation for transforming a z-score into a raw score. X, which is the raw score, equals the z of x times the standard deviation of x plus the mean of y. Now, we know already that the z of x for the 1r point is equal to 1. So in the equation, we'll substitute 1 for the z of x. So we now have a new equation. X is equal to 1 times the standard deviation of x plus the mean of x. Now, of course, 1 times the standard deviation is equal to the standard deviation, so we can just simplify the equation, and we get a new equation. X equals the standard deviation of x plus the mean of x. So we now know what x is equal to, and we'll write it up here. The unstandardized coordinate of the point, which we're calling x, equals the standard deviation of x plus the mean of x. Now next, we'll calculate the value of y, which is the second unstandardized coordinate of the point. Now again, we have a z-score to help us. The z of y for this point is equal to r. Now we can transform this z-score into a raw score using the same equation we used a minute ago. Y, which is the raw score, equals the z of y times the standard deviation of y plus the mean of y. Let's read that one more time. Y equals the z of y times the standard deviation of y plus the mean of y. Now, the z of y for the 1r is equal to r. So in the equation, we'll substitute r for the z of y. We now have a new equation. Y is equal to r times the standard deviation of y plus the mean of y. So we now know what y is equal to, and we'll write it up here. The unstandardized coordinate of the point y equals r times the standard deviation of y plus the mean of y. So now we know the unstandardized coordinates of both the point of averages and the 1r point. This is a very good thing we've done, because we now have 2 points on the regression line, and we know they're unstandardized coordinates. So we can now use these to calculate the line's unstandardized slope. We'll rearrange everything to make it easier to work with. And now we're going to calculate the unstandardized slope. The slope is equal to the rise between the 2 points divided by the run between the 2 points. So first, we're going to calculate the rise. The rise is equal to the y-coordinate of the right-hand point minus the y-coordinate of the left-hand point. So here's the y-coordinate of the right point, r times the standard deviation of y plus the mean of y. And here's the y-coordinate of the left point, which is the mean of y. So the rise is equal to the coordinate of the right point minus the coordinate of the left point. So the mean is equal, the rise is equal to r times the standard deviation of y plus the mean of y minus the mean of y. Now, I'm not sure I read that right, so I'm going to say it one more time. The rise is equal to r times the standard deviation of y plus the mean of y and minus the mean of y. Now, of course, the mean of y minus the mean of y is 0. So this part of the equation disappears, and we're left with this equation. The rise equals r times the standard deviation of y. So now we know the rise, and we'll write it in. The rise equals r times the standard deviation of y. Now next, we'll calculate the run. The run is equal to the x-coordinate of the right-hand point minus the x-coordinate of the left-hand point. So here's the x-coordinate of the right point, the standard deviation of x plus the mean of x. And here's the x-coordinate of the left-hand point, the mean of x. So the rise is equal to the coordinate of the right-hand point minus the coordinate of the left-hand point. So the rise, let's get this, the rise is equal to the standard deviation of x plus the mean of x minus the mean of x. Now, of course, the mean of x minus the mean of x is 0. So this part of the equation disappears, just like happened before, and we're left with this equation. The run equals the standard deviation of x. And incidentally, I made a mistake a second ago. I said this equation was equal to the rise, and I probably confused you. It's this whole thing is about the run. So the run is the standard deviation of x plus the mean of x minus the mean of x. Sorry, I just misread. So now we know the run, and we'll write it up here. The run is equal to the standard deviation of x. So at this point, we know the standardized slope of the regression line. The slope is equal, let's get it here. There it is. The slope is equal to r times the standard deviation of y divided by the standard deviation of x. And this equation should look very familiar because it's the same equation learned earlier today for the slope. So we've done it. What we've done is we've just demonstrated mathematically where this equation comes from. And let's give a summary of what we just did. First, we identified 2 points, 0, 0, and 1 r that are on the regression line. This point is the point of averages. This other point is what we're calling the 1r point. So second, we calculated the unstandardized coordinates of these 2 points. And we showed that these are the unstandardized coordinates of the point of averages, and these are the unstandardized coordinates of the 1r point. And third, we calculated that the unstandardized slope of the line between the 2 points is r times the standard deviation of y divided by the standard deviation of x. Now let's finish by thinking about a trusty ant who walks up the line between the point of averages and the 1r point. Now here's the unstandardized slope of the line. The rise is equal to r times the standard deviation of y. The slope. Excuse me. The rise, before I go on, the rise is equal to r times the standard deviation of y. The run is equal to the standard deviation of x. So, when the ant walks up the line between these 2 points, the ant travels sideways 1 standard deviation of x and travels up r times the standard deviation of y. Now let me show you what that means. As an example, for this regression line, r equals 0.50. So the 1r point is the point whose coordinates are 1.50. When the ant walks up the regression line between the 2 points, the ant travels sideways 1 standard deviation of x, and the ant travels up 0.50 standard deviations of y. Here's another example. For this regression line, r equals 0.80. So the 1r point is the point whose coordinates are 1 and 0.80. And when the ant walks up the regression line between the 2 points, the ant travels sideways 1 standard deviation of x, and the ant travels up 0.80 standard deviations of y. Now, here's a final example. For this regression line, r equals 0.30. So the 1r point is the point whose coordinates are 1 and 0.30. When the ant walks up the regression line between the points 0, 0 and 1.30, the ant travels sideways 1 standard deviation of x, and the ant travels up 0.30 standard deviations of y. Okay, so that completes our discussion of the unstandardized slope of the regression line and why it makes mathematical sense. Now finally, we're going to turn today to a new topic. We're going to talk about how regression equations are imperfect and how we measure that imperfection. Specifically, we're going to talk about the root mean squared error of the prediction for regression. RMS stands for root mean square. Yeah, root mean square, RMS. To begin with, we need to explain what a prediction error is. The predictions we make using regression aren't perfect. For instance, based on a man's height, we might predict that his weight is 170 pounds. But it's unlikely he really weighs exactly 170 pounds. Maybe he actually weighs 177 pounds or 164 pounds. The prediction is bound to be off by some amount. Prediction error is how much a prediction is off from the actual value. For instance, if we predict the man weighs 170 pounds and he actually weighs 177 pounds, then the prediction error is 7 pounds. In terms of arithmetic, prediction error is the difference between the predicted value and the actual value. So in the example I've just used, the difference between 170 and 177 is 177 minus 170, which is 7. Now, as we discuss prediction error today, we'll be using this scatter plot. It shows the IQ scores and grade point averages of 700 students. IQ is on the x-axis. Grade point average, that is GPA, is on the y-axis. The correlation between IQ and GPA in this sample of students is 44.6. The standard deviation of y, that is the standard deviation of GPA, is 0.304. And the red diagonal line is the regression line. So we're going to begin by focus on this student who's represented by a red dot in the upper right corner of the scatter plot. You can see the arrow at the dot. The vertical line helps us to see this student's score on the x-axis. So take a second. What is the approximate IQ of this student? Okay, so his approximate IQ, we don't know exactly, but it's about 135 or 140. And is that smart or dumb? Okay, IQ of 135 or 140 is very smart. Now, this orange circle shows the prediction point on the regression line for this student. For a student with an IQ of about 140, what is the predicted grade point average? Now, I want you to guess that. Take a look at this. And remember, it's just an estimate, just a guess. Give me your best estimate. If the student has an IQ of 140, what's the predicted GPA? Okay. The student's predicted GPA is 3.20, about. If you see the and what is this student's actual GPA? Take a look at the dot. That's right. This student's actual GPA is 3.80. So is this student a slacker or a hard worker? Okay, I'll let you think about that. Now, this line shows how much the prediction based on the regression line is off. In other words, the length of this line represents the error of the prediction. The student's predicted GPA is about 3.20, and the actual GPA is about 3.80. So 3.80 minus 3.20 is 0.60. So the error of the prediction for this student is about 6.60. Next, we'll focus on this student who's represented by the red dot in the middle lower region of the scatter plot. You can see the arrow pointing at that dot. Okay, so what is this student's IQ approximately? Okay, you got it? Okay, their approximate IQ is probably around 105. We can't tell exactly, but about. And what's this student's predicted GPA approximately? Well, it's hard to say, but the student's predicted GPA, if we look at the regression line, is about 2.90. It's where that round circle is, right? Uh, on the line. And what is the student's actual GPA? Well, maybe their predicted, uh, their actual GPA is around 2.20, 2.30, somewhere in there. So you might ask yourself, is this student a slacker or a hard worker? Okay, now what is the error of prediction for this student? The error is negative. Negative 0.70 or negative 0.75, about. An error is negative when the actual score falls below the regression line. Now, there's a mathematical formula we can use to calculate the error for any individual. Now, before I show you the formula, I'm going to introduce you to some new mathematical symbols. First is the symbol for the predicted value of y for individual 1. Okay? This is the value of y that the regression line predicts for a particular individual. The symbol for the predicted value of y has a little hat over it, and this hat means predicted value or estimated value. The little subscript 1 indicates that this is the predicted value of y for the first individual in the data set. And sometimes the predicted value of y is simply called y predicted. Now next is the symbol for the actual value of y for individual 1. And this is the actual value of y for this individual. When I say actual value, this means the score that the person really got on y, not just some prediction about it. The little subscript 1 indicates that this is the actual value of y for the first individual in the data set. Now, the actual value of y is sometimes called the observed value of y, or y observed. It's the same thing, just different names. In this lecture, I'll use all three names, the actual value, the observed value, or y observed. Finally, here's the symbol for the prediction error of individual 1. This error is equal to the actual value of y minus the predicted value of y for individual 1. The error is the difference between the actual value and the predicted value and tells us how much the predicted value is off. The prediction error is also sometimes called the residual. So this is the same scatter plot we were looking at earlier. It shows the relationship of IQ scores with first-year GPA in 700 college students. And we're going to use it to demonstrate how predicted error is calculated. First, we're going to calculate the prediction error for individual 1 in the data set, who is represented by this little red dot in the upper left part of the scatter plot. If we draw a vertical line, we can see that the IQ of individual 1 is 673. The symbol X with the subscript of 1 indicates the score of individual 1 on X. Now ask yourself, how intelligent is individual 1? Well, remember, average intelligence is 100. So this individual is quite a bit below average. The circle is the prediction point for people with an IQ of 73. And the y-coordinate of this prediction point is 2.61. So, for individuals with an IQ of 73, the predicted grade point average is 2.61. So now we've completed our first step. We now know that the value of y predicted for individual 1 is equal to 2.61. Next, we need to get the actual value of y for individual 1. Well, the actual value of y for individual 1 is 3.42. That's the actual GPA that this individual earned. So y observed is 3.42. So we now have y predicted equal to 2.61 and y observed equal to 3.42. Now next we need to find the difference between the two. That's the prediction error, E1. To find the error, we subtract y predicted from y observed. In other words, we subtract 2.61 from 3.42, and the answer is 0.81. So we now know that the prediction for individual 1 is 0.81 off from the actual GPA for individual 1. So we can enter the information for individual 1 in an Excel sheet. The worksheet shows that individual 1 has an actual value of 3.42 on y observed, a predicted value of 2.61, and E, the prediction error, is 0.81. Okay, now we're going to go through the process again as an example with individual 2, who's toward the bottom right part of this graph. Okay, now here's a question for you. Is the prediction error for individual 2 going to be positive or negative? Okay, so actually individual 2 is below the regression line, so the error is going to be negative. We'll see that in a second. So here's a question for you. What is the IQ of individual 2? Make a guess, just form a guess before I tell you. Okay, now the actual IQ is 127. So you can ask yourself how close you were to 127. Probably pretty close. Now, here's another question. What is the predicted value of Y? What is the predicted GPA for individual 2? What's the predicted value of Y? Again, just make your best guess. Okay, actually, the predicted value of Y for this individual is 3.09. Now, next, we need to find the observed value of Y. So what is the observed value of Y for individual 2? Make your best estimate. Okay, the observed value of Y is 2.41. This is the actual GPA of individual 2. So now we have Y predicted and Y observed for individual 2. And next we need to calculate the prediction error for individual 2. So go ahead and do this using the numbers that are written up here. Okay, here's the answer. The error is negative 0.68. That is, the observed value minus the predicted value equals negative 0.68. Right? That's 2.41 minus 3.09 is 0.68. Okay, so now we can repeat this process for all 700 students in the sample. For each student, we calculate a predicted value of Y and subtract it from the observed value of Y. And then in this way, we can get the error for each student. And we can enter them into an Excel sheet like this. Now, because we have 700 students, we will have 700 rows of data. And this slide shows the first 9 students. Now, once we've calculated the error for each of the 700 students, we'll want to find the typical size of the prediction error. For some students, the error is small. For other students, the error is big. But if we know the typical size of the errors, that gives us an idea how far off the predictions usually are. Now, how do we find the typical size of the errors? One idea is that we could just average the errors. That is, we could take all the numbers in the column marked E and calculate their mean. Unfortunately, averaging errors is an idea that sounds good but doesn't work. Now, if you've read the book, you'll know the answer to this question. Why doesn't it work to average the errors? Okay, here's why. It turns out that the sum of the errors and the average of the errors is always 0. Now, if the average errors, if the average of the error is always equal to 0, this should seem a little familiar. Where have we run into this situation before? That we sounds like we take all. Okay, we ran into this same situation when we were trying to find the typical deviation from the mean. We found out that it's useless to calculate the average deviation because the average deviation is always 0. However, statisticians have found a way to avoid this glitch by computing the standard deviation. As you remember, the standard deviation is really a kind of average deviation, but it's calculated, or a typical deviation, but it's calculated a little differently than the way we all learned to calculate the average in grade school. Now, it turns out the same approach that works with deviations also works with errors. It's our old friend, the root mean square. Now, by now, you're highly familiar with how to calculate the root mean square for deviations, which we normally call the standard deviation. And very quickly, I'll describe the steps that are used to calculate the standard deviation, which is also called the root mean square deviation. By now, you know the steps as well as I do. First, you square all the deviations. Second, you sum the squared deviations. Third, you find the mean of the squared deviations. This is called the mean square. And fourth, you calculate the square root of the mean square. This gives you the root mean squared deviation, which is also called the standard deviation. Now we can follow exactly the same procedure using prediction errors instead of deviations. And the result is the root mean squared error of the prediction, or the RMS error for short. First, we square all the errors. Second, we sum the squared errors. And this sum is called the sum of squared errors, or SSE. And third, we find the mean of the squared errors. This mean is called the mean squared error, or MSE. And fourth, we calculate the square root of the mean squared error. And this square root is called the root mean squared error of the prediction. Now, as you can see, the standard deviation and root mean squared error are calculated almost exactly the same way. But one method is for deviations, and the other is for errors. The standard deviation, which is also known as the root mean squared deviation, tells us the typical distance of individuals from the mean. The root mean squared error of the prediction tells us the typical distance between the observed values of y and the predicted values of y. Okay, now that we understand what the right root mean squared error is trying to measure, let's talk about calculating it. There are two ways to calculate the root mean squared error. First, here's the long way. And I'll show you using the sample of 700 students that we've been using throughout this lecture, this part of the lecture. First, you calculate all 7 errors using the procedures I showed you earlier. And the result is a list of 700 values of E that you put in a worksheet. You then calculate their root mean square. That is, you calculate the root mean square of the 700 errors. So first you square the errors, then you sum them, Then you find their mean, and finally you calculate the square root of the mean. And these are exactly the same steps you already know for the standard deviations. And this gives you the root mean squared error of the prediction, which is 0.272 for these 700 students. But this is exactly as the standard deviation of the errors if you calculated it that way. Because the root mean squared error of the prediction is just the standard deviation of the errors. They're the same thing. Okay, now I have a question for you. As we have just said, the root mean square error is just the standard deviation of the prediction errors. So what is the mean of the prediction errors? Okay, we told you this a second ago. The mean, the sum and the average or mean of the errors is 0, right? If we add all those errors up or average them, we're always going to get 0. Okay, now we've just looked at the long way to calculate the root mean squared error. Now, but there's also a short way. It involves the use of a formula which is given in your statistics book. And here's the formula, here's the formula. And let's try it out with the sample of 700 students we've been using in this lecture as an example. Here's the scatter plot again for the 700 students. And notice it gives you the numbers you need for the formula. The standard deviation of y is 0.3304 and r is equal to 0.446. So I'll put these numbers in the upper right-hand corner, so we have them handy when we need them. Now all we have to do is plug these numbers into the formula for the root mean squared error of the prediction. Here we go, let's plug them in. Okay, I've just plugged in the numbers. So take a moment to look this over, and then let me know if you have any questions about what I've just done. Well, actually, you can't ask me because this is recorded. So take a look and make sure you see what happened in that step. I just plugged in 0.446 for R and 0.304 for the standard deviation of Y. Okay, now that we've plugged them in, we just work this out. 0.446 squared is 0.199, so we substitute that. 1 minus 0.199 is 0.801, so we substitute that. The square root of 0.801 is 0.895, so we substitute that. And finally, 0.895 times 0.304 equals 0.272. So, using the short method, we've just found the root mean squared error is 0.272. Now, as you may recall, this is exactly the same answer we got using the long way. The long way and the short way give us exactly the same answer. They give us the same answer. So I have two recommendations for you when you calculate the root mean squared error of the prediction. My first recommendation is that you always use the short way to calculate the root mean square of the error of the prediction. The short way is very fast, and the long way is very, very slow. However, my second recommendation is that you make an effort to understand how the long way works. You will hardly ever use the long way to calculate the root mean squared error, but the long way is worth remembering because it shows what's actually going on. The root mean squared error of the prediction is simply the standard deviation of the errors. So the long way is important because it shows you how the root mean square error of the prediction is really just a new twist on something you've already learned about, the standard deviation. Okay, now before we finish, here's something interesting. I'd like you to calculate the root mean squared error of the prediction when the correlation between the two variables is equal to 1. Just do the calculations, but don't raise your hand yet or call out the answer. I want everybody to work this out, and I'll give you, let's say, 1 minute. Okay, in case it will help you, I think I can give you, here's the formula for the root mean squared error. So r equals 1. If r equals 1, calculate the root mean squared error. Okay, now let's go ahead and I'll show you what the answer is. By the way, the answer is 0. How do we get that? Well, first of all, if r equals 1, we're going to substitute that, plug that in place of r in the formula. So we get 1 minus 1 squared, and then we take that square root and multiply it times the standard deviation of y. But next, 1 minus 1 squared is 1 minus 1, so that's equal to 0. So we now have the square root of 0 times the standard deviation of y. Now, if we multiply the square root of 0 times the standard deviation of y, we get 0. So this tells us that if the correlation between two variables is 1, then the root mean squared error of the prediction is 0. And this makes sense. When the correlation between two variables is 1, all the points lie on the regression line. The predictions aren't off at all, and the error is 0. Okay, that finishes it for today, and next time we'll continue talking about regression.